I just want to start out here with a quick poll. Who out there would consider yourself a math person? Hands up. All right. I'm not afraid to show it. Now, what about you that are a little bit, I hated math in school. What are you talking about? Okay. I'm going to let you in on something. Me too. As a freshman engineering major, I got a 0 on a calculus exam. You try to beat that one. I answered every question. And I went to my professor after class, and I said, look, I'm going to have to drop your class. I'm going to have to drop out of engineering. I just can't do calculus. He looked at me, and he said, VanDieren, it isn't that calculus that you don't get. It is engineering that you have no clue about. In fact, what do you think I can measure on this 50-minute exam? I can't measure your mathematical creativity. I can't measure your ability to understand that there is an object like this gold horn here that has a finite volume, so we can fill it with paint, but an infinite surface area. We can never paint it. That I can't measure on a 50-minute exam, and just watch. One of these, you have those skills. One of these days, you'll become a math professor. This was as a freshman in college. I was like, ugh. A few weeks later, I took another exam from him, and I actually set the curve on that. And then after a while, I saw the light, and I switched my major to math. So what was it that my calculus professor was teaching me that day that turned my grade around in calculus and turned my interest towards math? The lesson he was teaching me is that mathematics is a creative enterprise. Understanding math is not measured by your ability to reproduce calculations, to mimic what the teacher has done on the board in the preceding weeks. Mathematical success should be measured by your ability to apply mathematical techniques to novel situations, for your ability to see things like this Gabriel's horn. This lesson's not new. In fact, it's similar to one that Leonardo da Vinci taught his art students. Copying without understanding the meaning is as an intellectual pursuit as that undertaken by a mirror. Okay, that's my paraphrasing. To call a painting art, we at minimum demand that there be some creativity and meaning to it. Without it, we might as well have a photocopy. To call a computation mathematics, we should also demand meaning and creativity. Without it, we might as well have computer output. Because the math that we see in the school system is often dictated by standardized tests, it sometimes lacks the meaning and creativity, and that's why I can stand up here and say that I hate math in school, but I love being a mathematician. What I want to talk about today is why and how we can break this misconception that math is not a creative subject, and I want to share with you some examples of how I augment the K-12 education of math. First, let's look at some examples of what goes wrong when we strip mathematics of creativity and meaning. Okay, that's not new math. That's the results of a fourth grader on an exam in a research study by Davis and Greenstein. She was asked to put in increasing order the numbers 6, 60, 600, and 6,000. And on the exam, she said, well, they're all equal. So the researchers thought this was a little puzzling because she was in fourth grade after all. And he asked her, which is bigger, 6 or 600? And she could answer that verbally, but on a written test that she knew was a math exam, she put herself into math mode, maybe had a little bit of math anxiety, and remembered a math fact that her teacher had taught her, that adding 0 doesn't change the number. 0 means nothing, and she applied it to the situation. Here's another example. Thomas Edison gave a mathematician, Princeton educated nonetheless, a problem. He gave him a light bulb and said, find the volume. Mathematician sat down with his pile of papers and started scribbling away calculations like this one here. And a couple days later, Edison walks by his office and he said, hey, do you have the solution to my problem yet? Mathematician was like, no, but look at all this work. This is a really complicated calculation. Edison grabs a light bulb, goes over to the sink, fills it up with water, and brings it back and says, go get yourself a measuring cup. We can't just rely on blindly using mathematical tools without understanding their meaning, not looking outside of the box creatively at solving the problems. Oops, okay. So these two examples are kind of mild. I mean, the girl eventually learned that 6 is not equal to 60, and this mathematician was slightly embarrassed. But I'm going to give you another example here that has impacted us all, probably in one way or another, and that's the crash of the world economy in some sense. One of the reasons for this was due to this formula. This formula was invented by mathematician David Lee. Yes, mathematicians actually do invent. There is new math out there. It looks like that. So he invented this formula, and it was used by money managers across the world to assign risk to mortgage-backed securities. So what went wrong is that the money managers were not aware, or did not make themselves aware, or didn't understand, or didn't think about it, that David Lee's formula was built under the assumption that 1, housing prices would continue to rise, 2, that the correlation between 2 houses defaulting was constant, and 3, that the default rate would remain low as it had been historically. These 3 assumptions are required for David Lee's formula even to make sense. But the money managers were using the formula in a context where these assumptions did not hold, where the formula was invalid. In some sense, they were making the same mistake our 4th grader was making by applying a math rule that they didn't quite understand the meaning of to a situation that it did not apply to. Okay, so that's why I think we shouldn't strip math from creativity and meaning. And as an educator, one of my roles is to treat mathematics as a creative and meaningful enterprise so that students will become effective problem solvers. This involves providing a setting for the students so that they can be comfortable to explore, discover, and make mistakes, maybe even get a 0 on a math test. So how do we teach a kid to be creative? It's really easy. We just sit back and watch them play. Think of building blocks. Here's a toy that children use their imagination to build houses, bridges, towers, worlds. They create patterns. They use blocks as abstract representations for other objects. You can use a block as a doll, a block as a car, a block as a weapon. They make up their own rules, and they answer the question, what happens if? And they do this all on their own without anybody telling them to do so. These actually are the same activities that a mathematician does, not with building blocks, but with our mathematical tools. We build, we create, we build worlds, actually. We create connections. We match patterns. We make rules, and we even break them. And we ask the question, what happens if, to explore our world. I challenge preconceptions about mathematics by presenting mathematics without numbers and symbols, because like our 4th grader, we see those numbers and symbols and we get put in math mode. So when I go into the junior highs and high schools, I do the whole presentation without any calculations. I want to focus on the creative side of math, the side that's graphical, the side that connects to the world around us. And I would like to share a few of these examples with you. So here is a game that I use to introduce students to the notion of a fractal. The way this game works is we have this triangle, we have a die, and what we do is we put a dot anywhere that we want inside this triangle, so I've put it here, just to start with, right? And then what we do is we roll the die, and after a roll, we will put a new dot on this board. So if we roll the die, we roll a 6, we're going to put a dot halfway between our old dot and the corner corresponding to a 6. We repeat this process, so let's roll the die again. We get a 3, and we're going to put a dot now halfway between our new dot and the corner that has a 3. And we can repeat this process again and again. We roll a 5, so we take our new dot and put a dot halfway in between it and the corner with 5. If we repeat this process for a long time, eventually we'll fill up this triangle with dots. But what's amazing is the entire triangle does not fill up. We end up getting something that looks like this, no matter what we roll. It's called Sierpinski's triangle. The reason I like this is, 1, this is new math. This is less than 100 years old. There is new math out there for us to explore, discover, and find out, invent. And students often don't see that because they're taught math that existed for a couple hundred years, many more. The second reason I like it is that this object's everywhere around us. In fact, I bet there are about 100 of them in this room at least. What's one thing we all have in our purses or pockets? We were supposed to turn them off at the beginning today? Cell phones, right? Remember those big old cell phones from like 15 years ago with the antenna that went out to here? Where'd those antennas go? Well, they still have antennas in the cell phones. Now they're shrunken down and they're shoved inside of our tiny little cell phones. Some of the shapes that those antennas are in fractal shapes, very similar to this one, if not exactly this shape. Another reason I like this example is that it leads itself to variations. We look at this construction and ask ourselves the question, well, why triangles? Why did we start out with a triangle in the game? What happens if we use a square? What happens if we use a circle? What happens if we use different shapes? Okay, why restrict ourselves to 2 dimensions? What if we go into 3 dimensions? And can I construct this picture in another way besides this random process? Sure. Just start with a big triangle and start taking out middle triangles as we go on. Oh my gosh, time's flying. At the end of my lessons, I let the students create these with beads. And I was going to talk a little bit about origami, and you all have an origami piece in front of you. We can go ahead and use the origami to teach students about pattern recognition, and you can see that you can put it together in a tetrahedron. I also teach some murder mystery with the kids. They solve a mystery using science and math. And I just want to leave you with a quote from David Pink, who says that the next generation is going to be we're going to need creators, empathizers, pattern recognizers, and meaning makers. Well, us mathematicians can fit that bill. We're not really known for our empathy, but we have the other three features. 3 for 4 is not bad, right? Better than 0. All right, thanks, guys.